This is a talk about RocksDB. So in the last year's Percona Live, this time, it's the first time we came here and introduced RocksDB and MyRocks. And I think in the past year, we have lots of new developments. I think we have, and this year we got a new RocksDB track sponsored by Netflix. I think, thank you for Netflix for sponsoring it. And in the past 4 years, I think that there's lots of new features. I'll introduce something, and also the community help us a lot. The last time this year, just take what platform RocksDB runs as an example. Last time, at this time, RocksDB runs on Linux, Java, Windows, iOS, and Mac X. So in the past year, the community, I guess some of you in this room helped that, made this RocksDB run on PowerPC, run on the Spark, Solaris on Spark, and MinGW on Windows. So this is all done by the community. So thank you for all your help. So today I'm going to talk about what's new in the past a year, and how it fits our longer-term plan of RocksDB. So this is our mission of RocksDB. We want to make RocksDB a fast and easy to use persistent storage engine for any workload on any hardware platform. So this is not the same as the description of RocksDB in our website or the GitHub page. So this is our eventual goal. We're still not there yet. We're going to keep working on this until it is achieved. So we call it storage engine now, not Key Value Store, but it's not because we change any interface, but because we hear from feedback from people like when you talk about Key Value Store, people tend to think point lookup only, no ranger lookup, no transaction thing. So we now call it storage engine. But yeah, that is our goal. Fast and easy to use storage engine for any workload on any hardware platform. In order to achieve that, there are three things we plan to focus on. First is efficiency. So the efficiency, so RocksDB is a big win for us in efficiency when we deploy MyRocks. We saved half of the flash space for MySQL when it's migrated from InnoDB to RocksDB storage engine. We will keep that. We will identify the next opportunity we can do to be more efficient. You will hear more of our plan on that. And ease of use is another focus we have. There's lots of options in RocksDB. If you're an expert, you can tune it to be very good performance, but the learning curve is kind of long, and the tuning is kind of takes some time. We will try to simplify this and help you to get started easily, tune it easily, and know what's happening inside easily. And performance. So performance has been a big focus for RocksDB. We pick the logo to be Cheetah by Juba because we say this is going to be a fast storage engine. So this is important for us. We'll keep that one. We will keep this general RocksDB performance going better, and also for some specific use cases people care about, we want to do specific improvement for them. So based on this, the big plan, we have something we worked on in last year. So I will talk to you about 6 features we introduced in the past year and how it fits in our plan. So I will introduce persistent cache, direct I/O, bulk loading, insert with hint, blob storage, and the Lua Compaction Filter. So first is persistent cache. So this is an efficiency feature. So we identified that after we use this RocksDB to to reduce the space amplification, we're trying to identify the next opportunity for efficiency gain. So next one we identified is to put more data on each host. Basically, use it in denser way. So it means that we use for the same host, same memory, same CPU, manage a larger SSD space. So for the same data you're managing, is going to be the number of hosts will be lower. So you will save something there. But the problem is like the ratio of memory to SSD is going to be lower. So currently, most of memory is used as cache. So some data we don't have to read from the SSD, read from the memory, and this ratio is going to be lower in this way. So the way we try to solve this one is to introduce another tier between these two storage tiers. So this is going to be some storage faster than this base storage. So if this storage is kind of, let's say, from the remotely from another host, and this one can be attached locally, so that can be much faster. And this storage needs to serve much higher throughput than this base layer. So with this new architecture, how we cache data needs to change. This is what currently usually most users do. So the most of memory are used by the cache. The smaller percentage are used as block cache, RocksDB's block cache, which cache the data for decompressed blocks. And the more data spent is used in OS page cache. It just automatically cache some part of the data in the files, and these are automatically compressed. This is a good combination, but in the future, the ratio, after this ratio changes, most memories probably will have to be used for uncompressed cache. And even that one can be not sufficient. So the most obvious use of this fast tier would be used as a cache, persistent cache, to cache whatever here. Some of the data are already here, the compressed one and uncompressed one in this persistent cache. So I will talk about this persistent cache as this feature, and also because we won't be able to rely on the OS page cache, that we can get rid of this layer. That's going to be the next topic. So the persistent cache. So persistent cache is basically cache some of the data on the database in this persistent layer. It is not new to us. For example, we have flash cache already still running in our MySQL production clusters in some host. Is caching data in the flash, and base layer is hard drive. And some other users use similar library. For example, dcache. This is not new. We're serving a similar use cases like them. The difference is we're totally user mode. This is not kernel module. This is RocksDB component. The benefit is you don't have to upgrade your kernel if you want to tune this cache. You don't need to worry about this upstreaming business of the kernel. And this optimized for RocksDB. There's closely integrate together. So that's the motivation of this project. To talk about a little bit about the implementation. So implementation is basically a log. When we need to cache some new block, we append in this latest file, a log file, in the end. So when we need to, when the cache is full, we need to evict something. We evict the whole file. It's just whole file is gone. So we take this approach because so the RocksDB is a compressed block is not aligned. It's variable size. So we want to squeeze this out as much as possible. We don't want to align the pages. So we'll wait we may waste some more space there. So definitely we need some index from memory, mapping from the block ID to the location of the block. Basically, in memory, there's a mapping table from block table to block ID to the which file it is, and offset and length. So when the eviction happens, if a file is gone, we also need to find all those entries and then evict it. So yeah, this is how currently this works. So the interface is easy. You can use it just as there's a factory. You call and give say which file system path you want to store this cache, the size of it, maximum size of it, and then it will return an object to you, and then you pass to RocksDB, and RocksDB will just use this automatically. So yeah, so this is the features in persistent cache. So you can give it a use if you have something like a hard drive and SSD combination, or some other slower and faster storage. This is something you can try. So next feature is direct I/O, just what I predicted. If for those people who not familiar with what direct I/O is, for Linux it's just all direct. I guess a lot of people know that. So other platform may have other interface. So if you don't use direct I/O by default in most cases, all the read or write go through this OS page buffer, page cache first. It does IRU the pages from the disk and then do this eviction business. And if we use direct I/O, read and write are directly go to the device and bypass this page cache. So when do you want to use the current RocksDB direct I/O? So you should to say you don't want to rely on the page cache. OS page cache is not needed for you. Is like the case I mentioned above. Like all the memory will be used by the uncompressed cache. So there's just no need. There's just no room for the caching any compressed data. And also the page cache also provide good things like read ahead or something like that. So you don't need to rely on this one. So it's like if you have your common query is like a long range lookup, that might not be a good perfect, but it's mostly your read is like point lookup or very short range lookup. That's not a big concern for you. So, and then what's the benefit of using the feature is, so if you don't want because page cache is shared across all the applications. If your service is co-located with other services, you don't want these to use the shared page cache to influence with each other, like someone else, and try to copy a lot of data, pollute the cache, and suddenly you get unexpected poor performance in your application, depending on RocksDB, and that's not good. Similarly, it can go the other way around. If you co-locate with another services and RocksDB suddenly scan a lot of data and the other services is slowed down, it's also not good. So it's also, they may get benefit by, because we bypass the page cache, the OS paging cost is eliminated. The CPU can be reduced a little bit, and some of the paging stalls can be avoided. And also, sometimes you want to have finer control of I/O size. Maybe you have a special I/O device that somehow have the I/O read and write. You want to do a special way. This can also help you to give better control. So this is how one you should consider use this feature. How to use it is pretty simple. There are just two options. So the use direct I/O reads controls whether your online read traffic bypass page cache or not. With that one on, all the reads will not read from page cache and not populate from there. And the second one, the option is to control the compaction process. I hope everyone knows what compaction is. Okay, so sometimes you still want to rely on the page cache for your online traffic, but you want to minimize this compaction's impact to the page cache. You can set this one on, so the compaction will go with direct I/O. So these two can be set independently. So this is status of the direct I/O. So we do plan to improve it further. As what I said, currently you only want to use it if you don't want to cache any compressed data. You don't need to cache any compressed data. But this is not this is not perfect. We do plan to for RocksDB to be able to manage compressed data too. So we can become a mature database system. So nobody has very few people should be able to need the page cache. That should be a default after this one. And we also need to do this data prefetching well enough to match what page cache can do for us. And some of the cache warming, compaction comes, compact all the data, they always gone from the cache. We need to do a little bit better pre-warming of this, the cache warming, so that your performance will get impacted if compaction is going on. So this is our plan of the direct I/O. So the next feature is the bulk loading. This is a performance feature. The bulk loading, I mean, from its name, you know that it's just to get to dump a lot of data in a database. So one people do need that. So one use case is popular in this web services development is to migrate a shard from a host to another. So lots of people have pretty small shards, and they co-locate it in one DB. They separate it by prefix as shard ID or something like that. Or sometimes they need to balance the traffic or other purpose. They will need to move one shard to another host. So that's just a big chunk of data moved to another host. This is candidate for bulk loading. And another one is people sometimes need to do some offline calculating from Hadoop, doing some page ranking or static score calculation for ranking. Calculate from offline storage, like Hadoop or something like that. They pre-sorted data, pre-shuffled data, and put into a data file, and they can ship it to the online serving traffic, to serving this online like ranking or something like that. And they can just simply ingest these files into RocksDB. This is another use cases can benefit from this feature. But of course, you can always achieve this one by simply getting these keys, right? And then insert this to RocksDB one by one. You can always do that. The bulk loading can be better in just simply inserting it in several ways. If you insert the data just as a user traffic, it's just it will share the channel with user traffic. You write to the log and then insert into this write buffer. That may slow down your write traffic. In some extreme cases, it may even like causing stalls, which is not good. And it's also the next reason that you will see later is like that the inserting to the RocksDB is actually pretty expensive operation. You will have some binary search or inserting a lot of that, and bulk loading can help you to get rid of lots of these costs, CPU cost, and it may have opportunity to improve read-write I/O too. So the interface is like that. The SST file is data file. the same data file as what is in the RocksDB, you can create a writer to the file and give a file name, and then you put your pre-sorted data one by one to this file, and then close this. So this file will be just a valid RocksDB data file, and then you can take this file generated there, and you can send it through network or to your destination places, and you call RocksDB DB ingest external file with the list of files you want to ingest, and the RocksDB will just put this data to the storage. So next I'll talk a little bit about how this is implemented. So it's a little bit word about how the writing works in RocksDB. So in RocksDB, when you insert a key and value, you first go to an in-memory write buffer called Memtable. Usually is implemented in skip list, and once this one is full, we dump this file to a data file in the file. Okay, so go back. So this is skip list is kind of index data structure. So that means think about the binary tree or big tree. So once you insert something, you have to insert to a sorted run and update the index. So it's to make sure the range lookup can go through for any after your insert, and your flush can be write to a file in sorted order. So this is actually go through the whole binary search. It's pretty CPU intensive, and after the flushing, you get a file. And in RocksDB, we have to keep this data in a shape of tree. So the data potentially will be compacted down, will be pushed down and merged down until the last level, which usually contains 90% of the data, and it contains some pretty keep a full data in some point of time in history, and this process going through this, just inserting, just merge down, and merge down. So this is a quite expensive process. But with this Bulkload interface, you first generate a file, and you probably already pre-sorted file or pre-sorted keys, or it's already pre-sorted, and then you don't need to pay this binary search inserting thing or sorting. So that's already saved some CPU. And another thing is, if the files happen to be not overlapping with any of the file in the last level, which is 90% of the data, right? We can just directly put the file there. It's just the job is done, basically. All those compaction costs will be avoided. We directly go to the last level. So this can be common if you generate from Hadoop is already pre-sorted. You already generated like non-overlapping file ranges, and that's already the case. But if it's not the case, then we will try to put the file in the lowest level possible, which is the valid levels we can put the file, so that we can reduce some of the compaction costs. So if we put in this level, we still need to merge this file down to the last level. But these things will be avoided. So you will avoid this some I/O. In most unlucky case, you cannot put in any level because it overlap with every level in Memtable, and we will flush the Memtable and put into as a new file. So in this case, is kind of a little bit unlucky, but you have to go through all the compaction, but it's still you avoid the CPU of doing the sorting. So it's usually not going to be worse than just inserting keys one by one. So yeah, this is the bulk loading. It's already a pretty popular features in lots of our RocksDB users. So can give you better this causes less CPU spikes when you load the data. So the next feature is insert with hints. It's another performance-related feature. So we have mentioned that inserting a RocksDB key involves the binary search in this binary searchable data structure. It's like, think about the B tree, binary search it, and find the location. There's a sorted one, and then put it there. But in some cases, we can do better. We can avoid this whole thing. So think about something like time series data. Think about the prefix A, B, and C are these entities, and this 1, 2, 3, 1, 2, 3 are this timestamp. You will insert keys in a way that for every entity name, A, B, or C, they're in increasing order. When take A as an example, although like A, B, and C are interleaving, the timestamp part for A is always increasing, like 1, 2, and 3, right? So that means like we can almost predict that the next position to insert the next A is in that green arrow, right? It's that position is going to insert. We need to insert the next key for A something. And similarly, if you look at B, so this timestamp part for B is increasing, and we can have a good prediction of the position to insert the next key for B something. Right? So the idea is if we can keep this some hint about where we can start to consider the position of each the entity A, B, or C, where we say the prefix, we can save this whole binary search by first check that position, right? So that is how this works. If we insert B3 in this case, without this hint feature, we have to do binary search from the top to the down, right? But if we have a hint to saying our last insert position is the B2, and then we come with this B3, and then we see, okay, for B something, the last position is B2, and we will first check whether the position after B2 is the right position. If it's correct, okay, we're lucky, we just insert it, and we're gone, right? No binary search. But if we're unlucky, we're not the case, no matter, it doesn't matter, we can always fall back to binary search and go back and find the correct position to insert, right? So that's the feature, insert with hint. So the implementation is exactly like that. We keep in-memory hash table from a prefix to a hint, which is some information about where we should insert data. So I mentioned that a simple hint can be just the position, but actually we're doing more sophisticated than that one. So even if it's not exact next key, we can do some locally search a little bit without falling back to the whole binary search first. So when we insert a key, we first abstract the prefix and then check this mapping and find a hint, and then use the hint to do the inserting efficiently, and then updating this hint table to this latest information after inserting, so that we can go in this inserting more and more one by one. So that's this features, how these features can improve this CPU overhead. So enabling this feature is easy. The only thing you need to tell us is how to extract the prefix, right? Only you know what is A, B, and C, how many bytes are A, B, and C. It can be 8 bytes, can be 12, can be 16. So you just implement a callback function, and which take this key as input and tell us what the prefix is. And we will go ahead and find this hint position for you. So currently this feature is not free. You need to pay something. So first thing you need to pay is the hash table has cost. They have, in average, 250 bytes per prefix we need to be used to store the hints and hash table. And also, so currently, RocksDB has a feature to have the concurrent Memtable insert. But this one is not compatible with this feature yet because it's not like technically impossible, but we need to synchronize the hash table hint and then resolve the conflict. We just didn't implement. Well, if you need it and you're interested in implementing it, you're more than welcome to just contribute to RocksDB code with this feature. So this should be just doable. Should be not very hard thing to do. So we run this benchmark with these features, and with a benchmark that's there's no compression. The only thing it does is inserting to Memtable with this the time series like workload. This improved the running time by 75%, and in one of our workloads is dropped the CPU is dropped significantly for this Memtable insert case. So this is actually when you think about this, it's actually more than just time series. As long as your insert position is like usually not very far from the last position, you can use this one. For example, if you're more likely to update the same key again and again, you're like not far from the last insert position, and you can use this feature too. So this actually, question, yeah.
Sorry, did it vary depending on the cardinality of the number of unique hash prefixes that you have, that performance?
Okay, the question is whether the performance is varies for cardinality. Yes, I think it's possibly. This workload related. The benchmark we run is, yeah, I think it varies. I think it depends on your workload. I don't have a very clear answer to this question. Yeah, so if you have any insert close to the last position, that can be beneficial. Yeah, this is the insert with hint feature. So next feature is DeleteRange. It's a performance feature. So delete key range is usually challenging for lots of RocksDB users. So there's two popular ways people implement it. One is to just read all the keys one by one to know what are keys in that range, and then to delete one by one. So this is the most straightforward way to do things. But the problem is the way RocksDB drop things, it doesn't just go ahead and drop the keys. It will need to first put some marker, we call tombstones, in this first Memtable or first files. And these tombstones will stay there for until it is compacted to almost the end, the last sorted run. The problem is it may cause iterating outliers. So in case you want to have a range lookup covering the range you want to read, no matter how many keys end up with in a range, maybe one or two, or even no result returns, you have to internally iterate all these keys to make sure that just no data is there. If you are deleting millions of keys, this iterator can be extremely slow. So this can be a problem. Another approach people do is to use this compaction filter feature. This is a nice feature that when we rewrite the data, we give user a callback for key and value to ask people whether they still need to keep the key or not. They can write a special filtering and to see whether the range within this dropped range, and then drop the key in compaction. And they can force the range compaction to force these keys to go through this filter. So the problem is, first is not atomic. This is rely on the compaction schedule. During this time, some keys are there, some keys are not, and also these codes are very hard to maintain. Right? If you think about how you write a compaction filter for that, you will need some registry to read from to see the range of this, and then you maintain the code, and that is very hard to maintain. So we have a new API, the DeleteRange, to make it easier. So this is very straightforward. You give a range of keys, start and end, and you say these keys needs to be done, and then just immediately after this operation, it's just gone for you. So what's happening inside is we will have a tombstone for range, and put them there, and this is gone. When you read here the range, you will say it's just dropped, and then you don't have to worry about this. And then in the background, these keys will be garbage collected in compaction through time. So far this is still have some limitation. So this is perfect for if you are doing a shard dropping. You just drop the shard, and that's perfect for you. But if you have very frequent small range deletes, this is still the performance may not be good for you. So if you are having this kind of use cases, you can talk to us offline, and we can discuss with you about how you can work around this and what to do with this. So this is the DeleteRange project. So the next is the Blob storage. So the motivation is like, so RocksDB works with blobs. You can even put gigabytes blob to RocksDB without problem. So the motivation is we can do even better. We can do, there's opportunities to improve the write amplification significantly for large blob data. So the usage is quite simple. You just, without, similar to open RocksDB, you open a Blob DB, and that's just you can just work as RocksDB, and it's just put Blob there efficiently. So the implementation is actually similar to this persistent cache implementation. So the Blob, instead of inserting to right-hand log and the Memtable, it just go to a log file, a Blob log file. Just append this blob in the end of these blob files. So after these files are full, it's just switch to immutable files, and we'll create new files to insert the blobs. But we cannot just keep going like that, because some blob will be dropped or deleted or phased out for TTL. Right? So we need to do some garbage collection. So the garbage collection is, before saying garbage collection, so similarly we need to lookup. So the lookup is done by an index stored in normal RocksDB. In normal RocksDB, we still keep a key, but the value is a metadata of the key, and just help people to locate where this blob is. Right? It's which file it is, offset the length. So the lookup would be just lookup this RocksDB and find this metadata and then read the blob out. So because the blob is large, so this DB is much smaller than that one. So this is going to be, no matter it's a read and write and space, it's going to be very small. So, but on the blob side, like the compaction will just compact this data, and that blob files has its own garbage collection cycles. So the garbage collection works like when we need to garbage collect the file, we go through this blob one by one and check whether we need to keep this. For any blob we need to keep, we append to active blob log file, and after, at the same time, we can just change this RocksDB's index position from the old position to the new one. And after all the blobs in these old files are either dropped or moved to a new file, and the indexes are updated, we can just drop the old file, and then the garbage collection of this file is done, and the old file is gone. So in this approach, this one can do the garbage collection much less frequently than normal keys. So we'll save some write amplification. So we run some benchmark. This is a DB bench with larger blob size. We run 1 kilobytes and 25 kilobytes. You will see with normal RocksDB, it takes the write amplification will be almost 10, but with this blob storage, the write amplification will be just not much larger than 1. Well, it's assuming that the compaction, garbage collection is really lucky that we don't need to rewrite much data. Yeah, so this feature is hopefully we can release in next release, which is going to be 5.5 next week, next month, I guess. And so far, it's only support very simple operations, just put and get iterations, iterators. I'm not sure. Maybe it works, maybe not. And there's some TTL you can give to these keys, but this put and get are guaranteed to work. So hopefully we can get it's improved over time, and maybe even integrate to this just normal RocksDB and to do it automatically. So the last feature I want to introduce is Lua Compaction Filter. It's this easy-to-use feature. Just recap about Compaction Filter. Already mentioned a little bit. RocksDB needs to keep merging existing files. Just taking 2 input file and merge it to one single sorting run. In this process, users can register a callback function. For each of these key and value, we ask user, please take a look at key and value and whether you still need it. So users can say, oh, I don't need this, and they can just, and we don't need to write it out anymore. So this is a very popular feature for something like TTL. The users can also say, I want the key, but please change the value to something else. This is also useful for something like data migration. This is pretty popular features among our RocksDB users. But maintaining this compaction filter is sometimes a painful thing. Because it has to be a C++ code and referenced in the code. This is if you want to modify the code, at the new one, you have to write some C++ or modify C++ code, and then possibly recompile your whole service and then redeploy it. Right? This is very complicated. It's also running as the same process as your service. So if there is some seg fault, your whole service crashes. Right? So especially it's painful for people who want to maintain a storage service to your users, especially for multi-tenant users. Think about you have multi-tenant users, they register a callback and then it crashes your whole thing, which is not good. So that's why we have this feature. So this Lua Compaction Filter, similar interface, but you can write in Lua. In Lua, you can say taking the key and value and see whether you still need it or what you want the value to be. So the reason we use Lua is this is scripting language, so it doesn't run in the same process as your service, and its performance is good for Lua. This is one of the best performant scripting language. And it's lightweighted. It's much easier to integrate and much better to write, easier to write than something like JavaScript. So that's why we use Lua as this callback. So using it is easy. So Lua Compaction Filter is just a normal RocksDB filter. It takes an option, that's the whole script, and then you can construct a Lua Compaction Filter with that script. And then just pass to RocksDB, and that should just work. So if you want to update it, you don't even need to restart your service. You can just only restart RocksDB with this new script. the new script you can transfer from network or your configuration delivery mechanism, and then just update it and then restart RocksDB. Or if you can deploy a new one with new DB, and you just get it there and have a DB run. That's just the Lua Compaction Filter. It can be a pretty cool thing if you want to build a multi-tenant service with this support. So I just want to recap what I introduced today. These 6 features, persistent cache to help us to get more efficiency gain with every host to manage more SSD, and direct I/O to bypass the OS page cache, bulk loading to be more efficient when you load a lot of data. So insert with hint help you to reduce CPU in Memtable insert, and blob storage to reduce the write amplification. This is another performance feature. And the Lua Compaction Filter to help you manage the compaction filter easily and safely. So that is coming back for this feature is a part of a larger plan to make RocksDB as a fast and easy to use persistent storage engine for any workload on any hardware platform. And we focus on these 3 things: efficiency, ease to use, and performance. So thank you for coming, and happy to take your questions. I think we still have.
One question. Since the GC of the blob storage just delete the whole blob file, is that you delete the whole blob file?
And the question is, the blob storage GC, is it just delete the whole blob file? So yes, it's just a move out blobs needed to another log and then remove the whole blob file.
So the worst case is that if the blob file contains a lot of blobs and 99% of them are not using, only 1% blobs still have reference. So this file is never deleted.
Okay, the question is, if 99% of data compacted is useful, do we waste a lot of data? So it's in theory it's possible, but it tends to be if your workload is mostly insert only, then we may not need to run the garbage collection that frequently. We can just wait for, like, say 10% wastes there and then run it. At least we get rid of about 10% of data. Question?
We're using the persistent cache is based on is done on a file basis. Why was that done versus on a block basis?
Okay, the question is whether the persistent cache the purging is done in file level instead of the blob level. Yes, it's because we didn't align the blob, so the block in the page level. So if we remove in the block level, we will have some hole of that's very size that is very hard to be reclaimed. Yeah, so actually, we are actually also considering other approaches too. But so far, this seems to work well in our benchmark. So it may not be a big deal for most of the RocksDB use cases. Okay.
Is that correct? There can be several key value pairs on the different levels of the LSM.
In separate key value in different what?
Of the different LSM levels.
Yes, it's possible. Yeah.
Okay. In the case of range delete, you just remove these SST files which are in the range of range delete, right?
So in the range delete, we put a tombstone, and if we merge down, because compaction is like compacting the.
This happens during compacting. There can be the case when the highest levels contains the information contains the same key value pairs as the lower levels. And when you do range delete, is it possible configuration when you
Yes, so this is the same for run delete and normal delete. So after remove some key, we don't remove tombstone. The tombstone still go down until we are sure that there's not likely any key covered in that range. Yes. Okay. There no any other question.
The Bulkload is maybe for migration or one-time loads, or can it be run like heavy query workload?
The Bulkload, the question is, does Bulkload only can be run in migration or initial loading? Yes, you can also use Bulkloading to do normal operation too. There's no constraint on it. Okay, thank you for coming. If you have any question, you can catch me offline, and I'll be happy to.